Hi, and welcome back to my videos for General Chemistry 2. Today, I want to tell you about the invention of the battery and the concepts that led up to it. Batteries make all kinds of technology possible today, from cell phones and laptops to electric cars, and they've gotten smaller and smaller and ever more powerful over the years. But as we'll see, the very first one was invented in 1799, and it's something you can build yourself at home if you want to. To get there, let's start by thinking about this very simple redox reaction. A piece of copper metal is placed in a solution of silver nitrate, which produces copper nitrate and silver metal. The first thing I want to point out is that silver nitrate and copper nitrate are both soluble compounds, so we really have this happening in our reaction. The silver nitrate and copper nitrate dissociate to give us ions. Notice that the nitrate ion appears on both sides of the reaction. That makes nitrate a spectator ion. Way back in your General Chemistry 1 course, you learned that one way of writing a chemical reaction is to drop out the spectator ions. If we do that, we get this. This way of writing a reaction is called the net ionic reaction. The reason why we might want to write the reaction this way is because it focuses our attention on the interesting part of the reaction. Usually, the spectator ions aren't the interesting part. Anyway, the first thing to notice is that this is a redox reaction. You can tell that because the charges on the copper and the silver atoms are changing. Thanks to the past couple of videos, we know how to balance redox reactions. So let's use what we learned to balance this one. At first, it might look like this reaction is already balanced, but as we'll see in a moment, it really isn't. The first step is to figure out the charge on each atom. Remember, neutral atoms have a charge of 0, so that's the charge on the copper atom and the silver atom. Meanwhile, the ions have the charge already assigned to them, so that's +1 for the silver ion and +2 for the copper ion. Notice that the charge on the copper went up, so it lost electrons, which means it was oxidized. The charge on the silver decreased, so it gained an electron, which means it was reduced. Now we'll separate the reaction into two half reactions, one for the reduction and one for the oxidation. From here on, balancing this reaction is really easy. All the elements are already balanced, so we can skip steps 3, 4, and 5. We do need to perform step 6, in which we balance the charges by adding electrons to the reactions. To balance the reduction reaction, we need to add 1 electron to the left side. And to balance the oxidation, we need to add 2 electrons to the right. Next is step 7. We need the electrons in the two half reactions to cancel out. Since there's 1 electron in the reduction and 2 in the oxidation, we'll multiply the first reaction by 2, which gives us this. Now we just add the two half reactions together to get the overall reaction, which gives us this as a result. That's it for balancing the reaction, but let's look at this one a little more deeply. This is a really simple reaction, but there are some pretty useful things that we can do with it. First, let's picture what's happening in the beaker. There's a piece of copper in the silver nitrate solution. The silver ions in the solution collide with the copper metal, and that's when the reaction happens. Pretty simple. But remember the half reactions for this process. Think about what these are telling us. The copper loses 2 electrons, and these are taken up by silver ions. So, 2 electrons are being transferred every time this reaction happens. Since there are trillions of ions and atoms in the beaker, that's a lot of electrons. It would be nice to be able to use those electrons to make an electrical current that we could use to power something. Unfortunately, that would be very difficult to do with the copper and silver nitrate in the same beaker. It would be great if we could put the copper in one beaker and the silver nitrate in another beaker. That way, the electrons would have to travel a distance in order to complete the reaction, and we could use those electrons to power something we want to operate. In fact, we can do that. Remember, the reactants are copper and silver nitrate, and the products are silver and copper nitrate. It turns out that the best way to make this reaction possible is to put all the materials containing copper in one beaker and all the materials containing silver in the other one. So the first beaker has a piece of copper metal and a copper nitrate solution, and the other beaker has silver metal and silver nitrate solution. Believe it or not, using this setup, we can get the copper and silver nitrate to react with each other even though they're in separate beakers. There's just two more things we need in order to do that. First, remember that what's happening in this reaction is that two electrons are being transferred from the copper metal to the silver ions. In order to make that possible, we need to give the electrons a way to get from one beaker to the other. That's actually easy to do. As you probably know, electricity can easily travel through a wire, so we'll connect the piece of copper metal to the piece of silver metal using a conductive wire. Think about what will happen. The half reactions tell us that the copper loses electrons, so the electrons flow out of the copper through the wire to the piece of silver metal. The other half reaction tells us that the electrons will then be picked up by the silver ions, which will then become neutral silver atoms. The two pieces of metal in this setup are called electrodes. The electrode where oxidation takes place is called the anode, and the electrode where reduction takes place is called the cathode. Since the copper is being oxidized, the copper is the anode, and the silver is the cathode. But there's still one more thing we need in order to make this device work. You might have noticed that there are electrons flowing to the beaker on the right, and nothing flowing back in the other direction. That's actually impossible. Charges can't flow from one place to another unless we give them a way to come back. If that were to happen, the beaker on the right would quickly build up a high negative charge from all the electrons that were flowing in that direction. But we know that each beaker actually remains neutral. How do we make that possible? The secret is to remember the one thing that we left out of this reaction, the nitrate ions. I told you the nitrate ions are spectator ions, so they don't take place in the chemical reaction, and we could leave them out of the balanced reaction. But that doesn't mean they're not important. If we give the nitrate ions a way to move between the beakers, they'll migrate away from the beaker on the right as the electrons come through the wire. For every electron that comes into the right side beaker, a nitrate ion will get pushed out of that beaker and into the one on the left. The connection we make between the beakers in order to give the nitrates a way to move from one to the other is called a salt bridge. Notice that in this example, it's nitrate ions that flow through the salt bridge, but that's just because we started with solutions of copper nitrate and silver nitrate. If we had a different spectator ion, like acetate for example, then that's what would go through the salt bridge. So, now we have a setup that transfers electrons from one beaker to the other. The electrons flow through this wire, so if we were to split the wire into two pieces and put an electronic device in the way, the electrons would have to flow through it, and that's basically what we're doing when we use a battery. Electrons want to flow from the anode to the cathode of the battery, but instead of just connecting them by a wire, we make the electrons from the anode flow through the circuits in our cell phone or other device before they can get to the cathode. Before we finish, let's think for a moment about what will happen to the reactants and products in this reaction as time goes on. This is an irreversible reaction, so as the reaction proceeds, the amount of reactant will decrease. Since one of the reactants is the silver nitrate solution, this is telling us that the concentration of silver nitrate in the right-hand beaker will slowly decrease. Eventually, it might even run out completely. When that happens, the reaction will slow down and eventually stop. That's what's happening when the battery weakens and then dies in your cell phone or other device. This kind of a setup, in which two electrodes are placed into two ionic solutions and connected by a wire and a salt bridge, is called a Voltaic cell. It's named after its inventor, the Italian physicist Alessandro Volta, who created the first Voltaic cell in 1799. You can see it in this painting of him. His Voltaic cell was a whole series of copper and zinc electrodes connected by salt bridges and stacked on top of each other instead of in beakers. We'll see how to make one of these in class. It's surprisingly easy. Volta is also the person who the idea of voltage is named after, and he also appears on Italian currency on the 10,000 lira note. This is another picture that includes his first Voltaic cell. Italy uses the euro now, so you don't see bills like this too often, but if you ever do come across one, they're worth about $526 at the time I'm making this video. Well, that's about all for today. In the next video, we'll talk more about voltaic cells and modern batteries, and find out how you can figure out the voltage that a battery can give you. That's a great application of redox reactions, so I hope you'll join me for that. Until then, have a good week.